On here, seems like a good chapter. I'll do that one still. All right. Well, last time we were talking about kinetics. And I'm imagining that had something to do with kinetics. That's what we talked about. We talked about rate laws, I think. There it is. Trying to remember. It's been a long week. I think we talked about rate laws, and remember, rate laws are all about pretty much the reactants, right? So those are really the only things that are included in the rate law. They have something that looks something like this. We got our A to our X, our B to our Y. Once again, as we talked about last time, this sort of X and Y are what are referred to as being the orders. And again, X would be the order with respect to A, and Y would be the order with respect to B. We also can add those orders together to get the overall order of the particular reaction, again, by just taking X plus Y or how many you may have, and that'll give you your overall order. Remember that rate laws are always found experimentally, which means you typically will be given a table like we had in a lot of those examples that we did last time. And usually in that table, you will have some different concentrations and some rates. And you'll usually have a number of different sort of experiments that were done. And we usually typically would do it sort of mathematically using sort of this equation, the rate 2 over rate 1 is equal to K, A to the X, and B to the Y. And as we talked about last time, what we're looking for when we kind of go to this table is we really want one unknown. So we want to find maybe two entries where one of the concentrations stays the same and this other one sort of varies. And we can put it into there. As we talked about last time, it really doesn't matter which one you put where in terms of top or bottom. But again, if you want sort of more whole numbers, usually if you put the one that has the larger rate up on top, that will usually give you more whole numbers when we're all said and done. If you do it the opposite way, again, you'll get more of a decimal type number. And remember that you want to put everything from each experiment all the way across, say on top, and then everybody from each experiment there across on the bottom. And that again will give us something like, 4 is equal to say 2x or something like that, which then we can figure out what x is here. If we get nice clean numbers, you could probably just imagine or figure it out by looking at it. But once again, if you don't have really nice sort of clean numbers, we talked about that you really can't take the natural log of both sides. It's one way to solve these. That again will bring the x down, and you can divide the natural log both sides there and solve it and get your 2 that you need. Once we do that, we then want to go kind of back to the table and then pick 2 other entries where in this case of my example here, we would want B to stay constant and we would want to kind of vary A and do basically the same calculation. Once we get those orders, we could write our completed rate law. And once we have the orders, we could also figure out obviously the overall order of the reaction. And lastly, we could then use our completed rate law that has the orders to solve for K, and we could actually figure out the value of the rate constant like we did in a number of those sort of examples, I think last time. We also saw in that last one, right, you want to make sure you look at the table, right, in case there's something like the times 10 to the minus 7 or something, I think it was in that one, to make sure that you do pick up on those things. Any questions on that? Yeah.
Calculating the rate constant, you should never have considering that either x or y will at least be equaling 1 at the very least, even if the other let's say x is equal to 1, y is equal to 0, like we saw in one of the example last lecture. You should never have to be able to not calculate that rate constant.
Yeah, so there is so for example, there are, as we'll talk about a little bit today, there are 0 order reactions, which basically means even in that situation, the rate constant would actually just equal the rate in that case. So even if you had, say, one reactant like A and it was to the 0 order and it's like a 0 order reaction, basically what that would do is basically just make that the rate that you look at would equal basically the rate constant. And basically it'll be equal to pretty much the rates that you see sort of in the table and stuff like that. So that is possible, but you should always be able to, regardless of sort of whatever orders they end up being, should always be able to calculate that rate constant. Yeah. Other questions? Okay, then now that we've talked about how to calculate rate laws and we talked about some different types of ordered reactions, we're going to talk about again kind of 3 most common order type reactions. And as I mentioned, usually overall orders, you don't usually get super high ones. Again, if you just think about logically, a lot of the reactions or equations that you've seen before, most of the time we have one reactant, two reactants, occasionally three reactants. So again, to get super high overall orders, a lot of times you would need a lot of stuff reacting at once, and that's typically not what most reactions are. So we usually have these sort of three orders, overall order type reactions that we come across, which is first order, zero order, and second order type reactions. So we're going to talk specifically about these guys here and the special sort of equations that go with that type of reaction. So the first one we're going to talk about is a first order reaction. And in a first order reaction, we could have a rate law such as this, where the rate's equal to K times A. And just like anything else, if nothing's written there, it is assumed to be 1, which means that this would be a first order reaction. When we would solve that rate law there for K and just look at the units of the rate constant, this is the typical units that we see associated with a first order reaction in terms of the units of the rate constant. And I think I mentioned a couple times last time, that's a really important thing to have in your head when you sort of see units associated with rate constants as to sort of what type of reaction it deals with. As I mentioned, they oftentimes will not tell you, blinking lights, hey, you're dealing with a first order or a zero order reaction or a second order reaction. Again, just in the problem, they'll give you that rate constant with the units, and they assume that you will know sort of what order reaction you're dealing with. So definitely knowing the units associated with the rate constant is really important. Now, we could get to this, by having one reactant like this, where obviously it is first order. We could also have two reactants, right, as sort of the question a second ago, where maybe one of them is first order and one is zero order, right? So that's another possible way you could get an overall first order type reaction that's occurring. The units are 1/seconds, but truthfully, the units are really 1 over some unit of time. We oftentimes think of it as 1/seconds because when we do experiments, for example, like next week or like you did maybe earlier, and we will do, a lot of times we do experiments in like seconds, right? We don't sit there a lot of times for days and years and weeks and stuff like that. But technically speaking, the units for a first order can be 1 over some unit of time. And again, the most common is 1/seconds, or reciprocal seconds is typically what we see with that. Now, when we look at sort of how A is changing with time, we can see that over a period of time, the concentration of A should start to decrease. So if we do a graph of the concentration of A versus time, and that's what the little T down here is, time, we will see really this sort of decrease with time of the concentration of A, which is what we would expect because this reaction should be heading to the product side and should be making products. Now, kinetics is all about graphs and kind of, let's see, straight line type graphs. So there is a linear relationship that you could get by going through this equation here. And this is what is sometimes referred to as the integrated rate law. And that's the integrated rate law here. And this is really the time concentration dependence of what's going on. And we have the natural log of A is equal to the natural log of A naught minus KT. And when we look at this, the natural log of A equal the natural log of A naught minus KT. This is, you could kind of think of it as your final concentration. This is your initial concentration, the guy with the little O at the end there. K is our rate constant. And T here is actually time, not temperature. So that is a lowercase t. So that is time. So this is the integrated rate law. Is basically the relationship of how the concentration changes with time based on the rate constant. Pretty much in kinetics, we like to graph things in a linear relationship, which means we could rearrange this equation as the natural log of A is equal to minus KT plus the natural log of A naught. And when we rearrange this equation in this form, This is basically the equation for a straight line. This is our y is equal to mx plus b, right? So that's your equation for a straight line. And when we do this relationship and we graph on the y, which is what that means, the natural log of a, and on the x would go t. We will get this linear relationship of a straight line here of the points where the slope of that line is equal to negative k. And that's what this is right here. That's the slope, right? By the way, b is the y-intercept, right? So that's what the b is, which is the y-intercept. So this type of relationship this graph here of the natural log of a versus time is typically the graph that we see for a first order reaction. And you do need to be able to recognize that as that's the graph that goes with a first order reaction, which is this. By the way, the line here has a positive slope value or a negative slope value. Negative. And that's why this is equal to negative k. Negative and negative turns my rate constant into a positive number. So if you were to graph this and take the slope off of the best fit line, you would get a negative value. And again, it is equal to negative k in this case, which will give you a positive value for the rate constant. Keep that in mind for the next experiment that's coming up, so you don't get all these negative numbers throughout your experiment here. So you'll end up with that. So there's also a half-life equation that we'll see in a couple of slides, but I'll just put it up here since we have all this going on. The half-life for a first-order reaction is the natural log of 2 divided by the rate constant. And if you do the natural log of 2 on your calculator, you will see 0.693. And that's sometimes that is how it's displayed in a formula. What is the half-life is pretty much what the name implies, is the time it takes for half of whatever you have to go away, basically, right? So if you started with 10 in terms of the concentration, after the first half-life, you should have 5. After the second half-life, you should have 2.5. After the third half-life, I need a calculator, but you keep going on 2, basically, and you divide it down there. So one thing about the half-life equation and the integrated rate law, a lot of times in some problems, you will need to use them sort of together. Not in all cases, but in a lot of cases, you might have to use them together. And this would be a situation, for example, like you're given a question where you're asked maybe about the time it takes for the concentration to change, but you're not given anything in terms of what the rate constant is, but they do give you something like the half-life. So you would use the half-life equation to figure out the rate constant, and then you'd use the rate constant in the other equation. So sometimes they're sort of used together, these equations. We'll see that a lot more probably when we get to nuclear chemistry, which uses some of these equations as well, that those two equations are sort of used together, but it can happen here as well. So there's several important things here for a first order reaction that you do need to remember. First off, those units of the rate constant is something that you should know. Obviously, you need to know the integrated rate law, which will allow you to figure out concentrations and times and how things are changing, and also the half-life equation and the typical graph that goes with a first order. So these are all really important things to know. I would say the graph on the left there, you should also recognize as a first order reaction. We will actually see that graph a little bit later on, but it'll look a little bit different for a different ordered reaction. Any questions on that? Also, a couple of things that you should keep in mind as you use these equations, and that is right here. And that is a unit type of thing that you want to be careful of, and that's between the rate constant and the time. So the rate constant, as we have saw yesterday or the other day and today, usually the rate constant has some unit of time in there. And obviously the time is a unit of time, and you need to make sure that those are always the same unit of time. So one's not like minutes and one's seconds, one's not days and weeks. So at some time you might come across a situation where the half-life or the rate constant is in a certain unit of time, and the time you're looking for might be in a different unit. So you got to make sure you don't have any unit problems as you do that. So that's something you got to watch out for as well. It really doesn't matter ultimately which sort of unit of time you choose, but they do have to be the same. And you probably would want to choose something where maybe that's what you're solving for, that unit of time. All right, so let's take a look at one here and try our math. The reaction of 2A goes to B is first order with a rate constant of 2.8 times 10 to the minus 2 reciprocal seconds. How long will it take from 0.88 to 0.14? So how much time will it take? So take a moment and see what you come up with there. Okay, so let's take a look here and see how we're doing. So a couple of things. They were nice enough to tell us it's first order, but if they didn't tell us first order, they did give us the value of the rate constant, and we do see the units of reciprocal seconds. So that is what should tell us that it is first order, and we obviously need to use the first order sort of integrated rate law. So again, a lot of times they will not tell you that. So we do have K given to us, which is 2.8 times 10 to the minus 2 reciprocal seconds. We want to know how long concentration of A to decrease from 0.88, which means that would be my initial concentration, and to go to 0.14, which would be my final concentration. So if I go with my integrated rate law here, the natural log of A is equal to the natural log of A naught minus KT. Here we have K, we have our initial and our final here. So we can solve for T in this case. So that would give me the natural log once again of our final, which is 0.14 equals the natural log of 0.88 minus our rate constant here. And that's going to be times T. Personally, I would punch this in my calculator as the natural log of 0.14 and then subtract as I bring this whole thing to the other side, right? To subtract it, basically. And I would subtract the natural log of 0.88. And that's going to give me something like negative 1.838279. I don't feel like rounding, minus 2. And that is negative 2.8 times 10 to the minus 2 reciprocal seconds times T. At this point, I need to divide, right, the rate constant to the other side. I'm not just dividing the rate constant, but I'm also taking the negative with it, right? So that's kind of important. The negative's got to come to the other side. Those guys are going to cancel, and that's going to get me here. We'll call it a lucky 66 seconds, as the units here will pop to the top, obviously, as we divide it out in that case. Question on that there. Yeah.
The arrow, what is that? I think it's
I'm subtracting it to the other side. Yeah, just mathematically. Sometimes people are not sure how to move things around. So that would be the best sort of way of doing it. Yeah. That's a bad knot circle like that. End of the week, my hand doesn't want to write anymore. Another question? All right. All right. So again, you want to make sure you understand how to properly punch these things into your calculator and rearrange things as well. By the way, again, if you have a display calculator, you would need to punch it in natural log, then the number. If you have a non-display calculator, you got to start the number, then hit the natural log, right? And if you're not sure which calculator, again, if you hit log and it says log, you have a display calculator. And if you hit log, it says error, you have a non-display calculator. So just keep that in mind. All right, so we talked a little bit there a second ago about the half-life. And by the way, if you're good at math, I guess, or okay with math, and you can't remember the half-life equation, you can substitute into our integrated rate law. For this, that divided by 2, and that will eventually get you down here if you solve it correctly for T in that case. But probably just remembering it might be easier. So here we're going to be looking for what is the half-life here of N2O5. If it decomposes with a rate constant of 5.7 times 10 to the minus 4. Okay, so looking at this, once again, if you weren't sure what the order was. That right there, which is our rate constant, which is reciprocal seconds, should answer this question here. Is why we do know that it is first order because of the units that we see associated with the rate constant. That means obviously here we would want to use our half-life equation, which would be our natural log of 2 divided by k. And popping that in there, natural log of 2 divided by, there it is, 5.7 times 10 to the minus 4 reciprocal seconds. That will get us about 1,216 seconds. Or if you want to do a little sig figs, about 1,200 seconds, I suppose, based off of that. So basically every 1,200 seconds in this reaction, right, we're going to lose half of the concentration that we started, right? Question on that one there. And that's what we see here is a graph again of our half-life. And after every half-life, we do kind of lose half of it, about 10 half-lives, not too much left at that point. Let's try another one here. The reaction here is first order with rate constant at 2.9 times 10 to the minus 4. Find the concentration of SO2Cl2 at 865 seconds if you started with 0.0225 molar. So take a few moments there, see what you come up with. Okay, so once again, let's take a look. Again, if they did not tell you, which is very common, we want to look here. We again see the reciprocal seconds on our rate constant, which tells us it definitely is first order, and we should be using our equation here. We do have our rate constant here, which is 2.9 times 10 to the minus 4 reciprocal seconds. We're looking for really our final concentration here of this guy. We do have our initial concentration, which was given to us, which is 0.0225. And we do actually have time here, which is 865 seconds. Now, when we look at our time and our rate constant, we are in the same unit of time in terms of the actual values there. So we don't have to worry about any type of units not working. We pretty much have everything we need on this side. So we could got the natural log of A. Will equal the natural log of our initial concentration of 0.0225 minus our rate constant of 2.9 times 10 to the minus 4 reciprocal seconds. And I'll squeeze my 865 in there, hopefully. There we go. All right, so we kind of clean up everything there on the right. We will end up with, let's see here, a little natural log of 0.0225 minus 2.9 to the minus 4 times 865. That's going to give us the natural log of A is equal to minus 4.045. At this point, we need to solve for A, right? So to get rid of the natural log, we need to take what to each side? Take the little E guy there to each side. When I do that, those guys are going to go away and going to have A. And if I pop that in there, we do leave the negative or non-negative there, whatever it may be. In that case, dare I say it is 0.0175 in this case, and this would be molar as it is a concentration, right? Questions on that one there? Also does make sense because I should expect my final concentration here to go up or down. Should go down, right? So again, here, if you did math wrong and you ended up with a higher concentration you started with, your reaction is going in the wrong direction, right? So it shouldn't be going in that direction. So again, those are things you want to think about as you kind of go through it there. Any questions on that there? All right, let's take a look then at this one here, which is actually instead of this one, let's do this instead of this one. Why not? Let's change it up. I'm just going to make something up on top of my head, so this should go really bad. Let's try this out. All right, let's say we have a radioactive isotope, which, by the way, does follow first order kinetics. And it follows that first order kinetics there. So say a radioactive isotope, we want to know how many seconds, why not, will it take for its concentration to go from 0.985 molar to, I'll go with 0.233 molar. If it has a half-life, why not? Let's go with 32 minutes. Why not? I hope that's everything you need. I hope. Let's give it a go. All right, so give it a go. I'm going to do it as well because, frankly, as you saw, I just made that right up right there. Well, hope for the best. Let's see how we do. I apologize for the weird numbers, probably, and in just a few seconds you're going to get. Let's see here. All right, so give it a go. See what you come up with here. Okay, let's take a look and see how bad I did. I think I did actually okay, perhaps. Let's see. All right, so all radioactive decay, as we'll talk about when we get to nuclear chemistry, does follow actually first order kinetics of what's going on. So we do know we're going to use our natural log of A is equal to our natural log of A naught minus KT. I see something about a half-life, so I'm going to throw my half-life equation in there as well. All right, so let's see what we got going on. We're looking for time here, and we want to know how long it takes for our concentration. So we have our initial concentration of 0.985. We have our final concentration here of 0.233. And we do have a half-life here of 32 minutes, right? All right, so we know that ultimately here we do want to solve for T. I have final and initial concentration. So this is a situation where I am missing the rate constant, right, in order to be able to actually solve what I'm looking for. But that's okay because in this case, they did give me the half-life here. So I do have the half-life, which means, well, as I was talking about earlier, we can use the half-life equation here to get the rate constant. And once we have the rate constant, we could put it into obviously the other equation, and then we'll actually be able to solve for what we're looking for. Now, personally, I like to think ahead here a little bit, and ultimately I want to know time in what unit? Seconds. My time unit here is in minutes. So I'm just going to convert it to seconds right off the bat. That way, when I'm done, I got the answer I need. I don't have to do another conversion or anything at the end. You could technically leave it in minutes. And if you did leave it in minutes, your rate constant would have units of minutes, 1/minutes. And when you would solve it with the equation, you would be in units of minutes. So you just have to do the conversion at the end. But again, just to kind of do it up front, everybody's in the right units when it's all said and done. I think there's still 60 seconds there. I hope in a minute. I don't know. You never know, It's like, well, how many hours are in a day? Yeah. That was not a trick question, by the way. 24, yes? All right, that's good. Just want to make sure. Whoa. Well, let's not go big math over there, all right? I say that because sometimes people, when they do like time, they go like, 60 seconds is a minute, 60 minutes is an hour, and they go like 60 days, 60, hours in a day type of thing. They got the 60 in their head. All right, so only 24 hours. Remember that. You don't want 60 hours in a day. That seems like way too much. All right, now that we have our half-life in there, we could rearrange that and solve for K. K would be the natural log of 2 divided by the half-life. And putting that in there, natural log of 2 divided by our 1920 seconds. That's going to get us a natural log of 2 divided by 1920. It's going to give us something like 3.61 times 10 to the 1, 2, 3, minus 4. Units here again are going to be our reciprocal seconds, right? So it's going to be basically 1/seconds in this case, which is what we expect here for first order. Now that we have our K, we now have really everything that we need to solve in that first equation. So putting our values into that first equation will give us the natural log of 0.233 equals the natural log of 0.985 minus our rate constant we just got there. and solving for T in this case. Now, again, as you can see, we got our seconds. So when we solve, we should be good. We're going to solve this just like we did like on the first one. I'm going to subtract this to the other side first. So I'm going to take the natural log of 0.233 minus the natural log there of 0.985. That is kind of like the deal, if you might be familiar with the natural log of a numerator over a denominator, right? And that's, by the way, where the units go away. They're basically dividing in reality of math when you do that. And that will give us minus 1.4416 equals negative 3.61 times 10 to the minus 4 reciprocal seconds times our T. Obviously, we're going to divide that to the other side and not forget the negative to come with it. And that will get us there minus 4. There we go. Divided by guess it's about a time of we got there 3.993 seconds. Too bad, I guess, if I put it right there. When we double check here to make sure I punch the numbers in right. 0.233 minus the natural log 0.985 and divided by our 3.6. Any questions on that one there? Yeah. Where did we go? Should be the one in the box there. 3.993. I hope. Yeah. If I didn't punch it in wrong, but I think I did good there. Let's double check. Now you might get a slightly different number if you did a little bit of rounding along the way, but you should get hopefully close to the right one here. My number there. That is about, dare I say, 66 minutes. Yeah. Ish, give or take. Which also makes sense if we think about it. Yeah. That's about 66 minutes, just under an hour. And this thing will be down to this concentration. Now, if we think about it logically, took 0.85 and divided by 2 one more time, right? Because that'll be about 2 half-lives. That's 0.24, so we're a little bit over 2 half-lives, right? 2 half-lives would be about 64 minutes, yeah? So that's 66 minutes, we're just a little bit over a second half-life, right? Any questions on that there? That's why I looked for, I did minutes earlier, my mic feels like a different number that I got earlier. Any questions on that one? So again, that's sometimes commonly used, the half-life equation and the integrated rate law together, and that's usually how you would use it in most cases. The half-life equation to get the rate constant, and then kind of go into the other guide there to solve it. Yeah.
So there's
What's that? The concentration should always be in these cases probably less than you started with, because it's a reactant, so it should be decreasing with time. So it should definitely be less than what you started with. So the rate of it will be dependent on obviously the rate constant in this case a little bit here. Yeah. Other questions? Yeah. What's up?
That's a half-life, 32 minutes.
Yeah. 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 So basically this thing went through definitely 2 half-lives, and then it was on its way to its third. Basically, it's just past the second half-life, right? And you can see that it does make sense if you take the initial concentration and divide it by 2 once, and then divide it by 2 one more time, you'll end up with 0.24. That would technically be the concentration you would have after the second half-life, right? At 0.24. But we're down to 0.233, which means it's past the second half-life, right? In order to get to the second half-life, that would be 64 minutes, and this is 66 minutes. So we're just past that second half-life. Yeah. Other questions? All right. I wasn't too bad making up numbers on the fly. That was pretty good. All right. All right, then let's talk about another order reaction, which is a second order reaction. And a second order reaction can be achieved obviously one of two ways. You could have obviously one reactant like we have here where it is second order. You could also have obviously two reactants where they're both first order. You could also have two reactants where one's second order, one's zero order. So there's a few different ways that you could achieve sort of a overall second order reaction. If we took the rate law here and solved for K and just looking at the units, we see again an important unit here, which is the units we saw a number of times, I think, the other day. These are the typical units that we find for the rate constant for a second order reaction, and it is 1/molar seconds. And again, that time part doesn't necessarily have to be seconds, but it is sort of the most common unit. But it's basically 1/molar, some unit of time, basically with it. Now we do have a integrated rate law that goes with a second order reaction, which is a little bit different looking than the first. It is 1/A is equal to 1/A naught plus a KT. And in addition, we have a half-life equation here that is 1/K times the initial concentration in this case. And that means that unlike a first order, which is independent of the initial concentration that you have for that reaction, the second order's half-life is dependent on the initial concentration. So it does have an effect on the half-life of this particular reaction. We can also take this equation here, which is all our same things, our final concentration, initial concentration, rate constant, and time. And we could rearrange this equation as this: 1/A is equal to KT plus 1/A naught. And this would be the form of our second order equation in a straight line of y is equal to mx plus b. That means that the graph, the linear relationship that we see for a second order, will have 1/A on the y. On the x, we would graph time, and this will yield us a linear line and a linear relationship in this case, where the slope of this is actually equal to k. The reason the slope of this one is equal to just k and not negative k is the slope of this line should give you what type of number? Positive number. So you have a positive number, again, giving you that positive value for the rate constant here. So again, that initial concentration in this case has an effect on that half-life. And if the initial concentration is larger or increases, the half-life will go up or down. It will go down, right? Because you take 1 over a larger number, right? You get a smaller number, right? And that basically is a constant, right? So all other things constant. If this guy increases, this guy is going to actually go down, and vice versa. Obviously, if it's a smaller concentration, then it'll actually go up. So that's sort of the relationship that you see in terms of the half-life. Just like the first order, several things that you do need to be aware of. Obviously, the units that go with our second order, obviously our sort of time concentration dependence, our half-life equation, and once again, our graph that goes with it. So you do need to know those things for sure. Any questions on that one there? The last type of reaction we're going to talk about, which is common, is zero order reactions. And in a zero order reaction, we will get a rate constant where perhaps if you have one reactant, it's zero. And if we solve for it, because that one reactant is zero order, as we talked about, is going to be 1, which means the units of the rate constant for a zero order reaction is actually the same as you see for the rate, which is molarity over seconds. So that is the units that we typically associate with a zero order reaction. We have an integrated rate law, which looks just like the first order one, except there are no natural logs. So it's just basically the same one without the natural logs. We also here have a half-life equation that is the initial concentration is divided by 2 times the rate constant. Just like the second order reaction for a zero order reaction, the initial concentration does play a role in the half-life. And like all the other sort of equations, we could also rearrange this equation in the form of a straight line, which will look something like this. No natural log though. There we go. A naught. And once again, that is going to be our y is equal to mx plus b. And we'll put that in there. Our y is equal to mx plus b. And that again tells us what we're going to graph. Concentration versus time will give us a linear relationship in this case with a negatively sloping line. And again, the slope here would be equal to negative of the k, which will turn our k. This graph here is the exact same graph that we saw for first order, except in a first order graph, it is not a linear relationship, right? This one is a nice linear line. First order was the decreasing with time graph, right? So that is how you can tell if you're looking at, say, this graph and you have a linear line or a linear relationship, it's probably going to be a zero order reaction. Again, if you see more of that kind of decreasing with time like we saw with the first order, it would be more of a first order sort of reaction. So it is really the same graph that we sort of see sometimes with first order, but it gives you something different if it is zero order, and it should give you that linear relationship. Just like all the other ones there, those are the four things you need to know pretty much. Again, units for decay, equations, half-life, and integrated, and our graphs here. Any questions on those there? All right, let's try another one here. I think the reaction here is second order with K. Initial concentration is 0.01 after 50 seconds. And it goes to 0.001. What is the second order? So a little second order equation would be good. Remember, this is the one that has a plus and not a minus in this one. We have our initial concentration there of 0.01. We got our final concentration of 0.001. And we have our time here, which is 500 seconds, I think. All right, so we got everything we need since we are looking for the rate constant here. So we'll go 1 over 0.001 equals 1 over 0.01 plus our k and our 500 seconds. Again, I'm going to subtract this to the other side, right? So a little 1 divided by 0.001 minus 1 divided by 0.01. That looks like a 900 there. And that's going to equal k times my 500 seconds in this case. And by the way, that would be 1 over molarity at that point, I believe. And we will then divide our seconds over there. And we will then end up with, if I don't do 5,000, we'll end up with 500. There we go. We'll end up with 1.81 over molar seconds is equal to our rate constant. As obviously here, I forgot to put my m's there. We got 1 over m basically. Question on that one there. So once again, you do need to know these equations. Yes, the units associated with it, the graphs, and the half-life equations. Any questions on that there? Okay. Here's a nice table. It sort of summarizes all the formulas here for the different orders along with the half-life equations. And again, you are responsible for these guys here. Yeah, so make sure you do know. And also, as we talked about graphically, which is a very common way that we sometimes determine the order of reaction, and really the not next experiment, the experiment afterwards, pretty much what you're going to do. We're looking at those graphs and understanding those graphs as to which one's more linear will allow you to figure out first order, second order, and zero order. By the way, when we do a graph, right, and we do a best fit line, what do we look at to decide what's most linear? We look at R squared value, yeah? Like if you graph it on Excel or something like that, right? You look at the R squared value, and one closest to 1 is most linear, right? And away from 1 or less than 1 is not so linear. So that's usually when you do something like this and make some graphs, you would look at the R squared value that you would get when you graph on something like Excel, and the one closest to 1 would be the most linear and tell you basically the order. Also a reminder that there might be some questions definitely out of this chapter that you might have to go to the computer and make a graph in order to answer the question. So sometimes that does happen. Any questions on any of that? By the way, yeah. Why is it again? It's positive because of the relationship that we get when you graph that relationship. We actually get a positive sort of slope that's happening in that line. All that's the only one in second order that you get sort of a positive slope heading in that direction. For zero and first are heading in that direction, which is negative, which is why it sort of incorporates into that equation. It has to be negative to end up ultimately giving you a positive K value. Other questions? Now, what happens if you had like percentages? Could you put percentages into these equations? The answer is actually you can put anything you want into these equations. You can. So you can actually do grams and grams. You could do any type of units. Although in this chapter, we mainly talk about molarity and stuff like that. Later on, for example, when we do get to the nuclear chemistry chapter, we use units like grams, milligrams. We use radioactive counts per minute. So you could use actually any type of unit in that concentration one. It works the same way. But, you know, if you had a problem, for example, that said, you know, how long would it take for you to have only like 40% left of what you started with, right? What would you put into that equation? Say it was first order. For our initial, we would put 100, right? Because that's what you started with, right? And for our final, it would be 40%. Or you could do 1 and 0.4 or whatever way you want to do. It's the same deal. So sometimes you will be given perhaps problems where they talk about percentages and stuff like that, and you can't put percentages into these equations and solve for, you know, whatever you're solving for in that sense. You just want to be careful when you read those percentage type questions. You know, is it like 40% of what you started with you have left, or, you know, do you still have 60% left because you only lost 40%? So sometimes they're kind of a little tricky in terms of the wording. But usually when they say something like that, they're meaning like that's how much you have left, just like the 40% or something like that. Any questions on any of these specific order type equations? All right, then let's talk a little about energy and equations. These are two energy diagrams. The guy on the left there is our exothermic reaction, and the guy on the right is our endothermic reaction. And a reminder, right, the reason the guy here on the left is our exothermic is because our reactants are higher in energy, right, than our products, which means overall for our reactants to get down to our products, energy has to be released, right? And that is basically what exothermic means, some type of process where energy is being released. Opposite is true over here. This is our reactants. That's our products. And in this case, our products are higher in energy than our reactants, which means in order to get there, energy has to be absorbed or sort of put in if you want. And that is an endothermic process, right? We absorb energy. When we look at this, the difference, right, between the energy of our reactants and the energy of our products, right? This difference in energy is what? What do we call that? Starts with a E and an N and a T. So yes, it's the change in the enthalpy, right? That is the change in the enthalpy for that particular reaction. As you remember, right, delta H of the reaction is delta H of our products minus the delta H of our reactants, right? And in this case, our products are lower in energy, right, than our reactants, right? Which means this number here is going to be smaller than this number, which means that will give you what type of sign for delta H in an exothermic? Negative, right? That's why we end up with a negative value, right? Same thing here. If we took our energy of our reactants and our products here, the difference, that also is the delta H for this reaction. And in this case, our products are actually higher in energy than our reactants, which means in that case, this guy's going to be larger, this guy's going to be smaller. And when you subtract those two, you will get a positive value there for your delta H. And that's why, again, one's exothermic and endothermic as well. Now, in order for a reaction to take place, there's several things that actually has to occur There's collisions that has to occur, so things do need to kind of come in contact with each other and hit each other. They actually do have to hit each other sort of in the right location. The active spot of each of them has to actually hit each other. And they actually has to hit each other with the right amount of energy for a reaction to take place. So not all collisions, when things just come together, will result in products being formed. If you don't kind of hit each other in the right spot or hit each other with the right amount of energy, you will not make any products in terms of the collisions. Now, speaking of energy to make our products, that is the hill that really the reactants has to climb in this diagram, right, to get to the other side. And that is our activation energy, which is abbreviated E of A. And that's the minimum amount of energy that's required for a reaction to take place. It is really the energy barrier that those reactants has to climb, as I mentioned, basically to get to the other side. Now, what is happening in a chemical reaction is all we are doing are breaking bonds, which is all electrons. So we're just going to be breaking a bunch of bonds, and then we're going to be making some bonds on the other side. So it's all involving electrons that are happening. So as the reactants start to progress up this hill, what we start to have is some bonds starting to be broken. And then we also have some bonds that are starting to be made at the same time. So we're starting to break some bonds, starting to make some bonds as it sort of crawls up the hill till it gets to the very top here. Very top of the hill is also referred to as the, anyone? Transition state. Yeah. Yeah, I teach that in 50 anymore. At the top of the hill, there is the transition state, is the highest point in energy. And we have this little complex here, which has this little arrows and stuff on the top there. That little guy there that's in the box is sometimes referred to as the transition state complex or activated complex. So in chemistry, right, if things are really high in energy, which is essentially where this is, right? This is the peak of energy. Is that a really stable thing or an unstable situation? Do things like to be in high energy or low energy? Yeah, that's really the point of everything that happens in chemistry is to overall kind of bring everybody down into a like kind of a lower state of energy. So because this is really the peak of the energy in terms of this reaction happening, that transition state complex is a situation where you have a substance that has partially broken bonds and partially made bonds at the same time. So it's really at that transitioning state of about ready to become products. They usually do not hang around a really long time because they're quite unstable because they're the highest point of energy. They really quickly want to kind of drop down the hill to the other side. So a lot of times they're very hard to isolate. For example, in a reaction, you want to isolate that intermediate in between. It's very high in energy and usually doesn't hang around a very long time to make our products. We have the same thing happening on our endothermic process as we go up the hill to the other side. Now that activation energy barrier there has an effect obviously on the rate of a reaction, right? So if I have a really big activation energy, most likely my rate's going to be slow or fast. So if I have a really large activation energy, as I said, I think, right, it's going to actually be probably slower, right? It's a bigger hill to climb, right? So if you think about yourself walking up a big hill, you have a really big hill to get to the other side, or a small hill, probably you're going to get up to the other side on the smaller hill, right, faster. And there's going to be a lot more people that's going to choose the smaller hill, right, to go to the other side. And that's the same idea here with a reaction with a smaller activation energy. You're going to have a greater proportion of molecules that have enough energy basically to make it up and over to the other side. And that's going to basically increase your rate of your reaction, right? And as opposed to one where you have a much larger sort of hill, there's going to be probably a smaller proportion of molecules that have enough energy to get up and over basically to the other side. Just in looking at these two diagrams, we can see that the endothermic typically has a larger hill, right? Because it needs to absorb energy, right? Overall, to get to the other side. So that's why we sort of see that big hill. As we talked about a little bit earlier, one way that you could speed up a reaction is adding a catalyst. And ultimately what a catalyst does, as I mentioned, is it finds an alternative pathway, sort of a more efficient pathway for that reaction to take place. And by doing so, instead of having to go up and over the hill, maybe it just finds the trap door like in the cartoons, right? The roadrunner opens the trap door, goes straight through, right? The coyote chasing him hits the wall, right? Because he's got to go up and over. So you find like the trap door, it takes you right through the mountain to the other side, much quicker, obviously, than going up and over. So ultimately, what a catalyst does is it's able to actually lower this activation energy. So when a catalyzed reaction, what happens by finding that more efficient pathway, it will actually lower the activation energy when we have a catalyst. And the result of that is you now will probably have a lot more molecules that have sufficient amount of energy to get up and over to the other side. And that will usually result in an increase in the rate of the reaction because that energy barrier has now dropped down a lot lower than where it started. And that's going to allow a lot more everybody to get to the other side. Any questions on that there? All right, so let's talk a little bit about the effects of temperature on the rate of the reaction. That's the Arrhenius equation. This is one version of it, and we'll see a couple different versions of it here. This is T is the temperature in Kelvin. This is the gas constant that actually involves energy. It's the 8.314 version of it, not the one you use in the ideal gas law. So this is the 8.314 joules per mole per Kelvin version. A is the frequency factor, and as we'll talk about, it's basically the proportion of molecules that really do possess enough energy to kind of get over to the other side. And obviously, E of A is our activation energy, that extra energy that's needed for molecules basically to start reacting. So this is one version of the Arrhenius equation, which we don't probably use too much, and we'll see sort of another version of it here in just a second. But let's talk a little bit about some of these things. That energy barrier is in all reactants or reactions, and that activated complex, which is what we see at the very top there, is a very high energy species, which has, again, those partially made bonds, partially broken bonds. It really is why they call it a transition state, because you're really at that point where it's about ready to break apart and reassemble sort of correctly on the product side and transition over to the products as we go to the other side. And that's what we see, for example, here in this reaction. All we're actually having in this case is a rearrangement of what's going on. The C and the N are going to actually switch places. But in order to do that, you actually need to break these bonds here, and you actually need to make some new bonds over here between the carbon and the other carbon, actually, in this case. So as this thing starts to progress, what happens is we start to get these guys starting to break bonds and also starting to make bonds. So we get this sort of transitional state where this guy's going to be able to basically flip around and move the nitrogen out that way. This guy will move in this way, and we'll ultimately get here our rearrangement that happens as we go from one side to the next. And there actually is some breaking and remaking of these bonds as it goes up and over to the other side in this case. All right. So when we look at this equation, probably one of the ways that we will use it more often is in this version of it, where we basically go through it and take the natural log of everything. And this version of this equation is sometimes I refer to it as sort of the graphing version of this equation. This is the equation basically in the form of a straight line. This is y is equal to mx plus b. And usually this is probably the version of the equation that you'd use. But the relationship between the rate constant and temperature, we could actually see on this graph here to the left. What we see is at a lower temperature, we have a much smaller rate constant. And when we increase the temperature, as we would expect, we do see the rate constant start to increase as well. And that would be what we would expect to happen as we increase the temperature. We're adding more energy. More energy is going to allow a lot more people to get up and over to the other side. That's going to be the rate of the reaction, as opposed to, again, at a lower temperature, there would be a lot less people that have enough energy to get to the other side. So this version of the equation on the bottom is really the one where we would use for a graphical way to figure out something like the activation energy. And what we would graph is pretty much what it shows here. On the y, we would do the natural log of k. On the x, we would do 1 over the temperature, and that does need to be in Kelvin, by the way. And that will give us a slope that's equal to minus E of A over R. So this should give us a linear relationship. So if you have a bunch of K values and that goes with a bunch of temperature values, you could do this graph here and you could use the straight line that you hopefully should get and be able to figure out basically the activation energy through a graphical purposes of it. And that is what we kind of see here. Once again, this is going to be y is equal to our mx plus b. So on the y is our natural log of k. On our x is our 1 over temperature in Kelvin. Yields me a straight line where the slope here is equal to minus E of A over R. That line right there is what type of slope again? A positive or negative? And that is why the negative value is here, because your activation energy actually should end up being a positive number always. So the activation energy should always be positive. You look at the graphs we just saw, this is the activation energy, right? So that is the hill that they have to climb, and it is a positive value. So when you do solve for activation energy, it should always be a positive value. And that's because, again, your slope value here will be negative, and this negative is important. So basically, it's very simple to sort of figure out the activation energy of reaction through this graphical purposes. You basically would graph the line, get the slope, and times it by 8.314. And that would give you the activation energy here, by the way, in units of joules, because that is 8.314 joules per Kelvin per mole. That is basically where the units of joules come from. I will say in most cases, though, the units of activation energies in kilojoules is usually most of the time the units that you see. And that's going to be really important when you do some calculations with it, because you will be using R and the activation together in the same calculation. And it's a very common mistake that people make, that they leave one in kilojoules and one in joules. And again, you're going to be off by that factor of 1,000 if you do that. So you want to be careful of the units as you kind of go through it here as well. So that sort of exponent factor, or that frequency factor, as I mentioned, again, is that proportion of molecules that do have enough energy to get over that energy barrier. As we talked about there, again, increasing that temperature does increase the average kinetic energy of those molecules, and that's going to give you probably a greater proportion of guys that can get to their side. The end result of that, as we've been talking about, is going to be that the rate's going to basically increase. And obviously vice versa on lowering the temperature. Again, we would see a lower proportion of molecules that have enough energy to get to their side. As we saw earlier on the other day, typically if you raise, for example, the temperature of a reaction by 10 degrees Celsius, for a lot of reactions, that's enough to really double the rate. And again, you're just going to have twice as much guys that could get to the other side. And that's what we see here. These are the same reaction at two different temperatures. Temperature 2 here is our red curve, and temperature 1 here, which is a lower temperature, is our blue curve. And this is our activation energy. And what we see here is at the second temperature, which is the higher temperature, that is how many molecules have the ability basically to get up and over to the other side. We look at just the lower temperature reading there, it goes to about here. It only has about that much molecules that have enough energy to get to the other side. So this again demonstrates that increasing that temperature does see an increase in the molecules that have enough energy to get to the other side. And that is our Plotty equation there. That will give us our straight line. All right, I think it's a good place to stop, actually. So we'll lay it up there.